I hope this is informative for everyone, and like Hannah said, we can have some questions and answers at the end. You'll also be able to get my contact information to send me an email with any questions you might have. It's a fairly complex subject, and I'll try to cover it as much as I can in this. We're basically just going to cover water pumping with direct PV. I'm not really going to go into running water pumps off battery systems or off inverter systems. That's pretty much done as just a standard load on any kind of power system. So I won't really go into that, although a lot of the information I will be presenting about, sizing pumps and the type of pumps and whatnot will be somewhat relevant in that field too. But we'll just be primarily discussing direct water pumping with PV without batteries or inverter systems. So let's get started here. PV direct pumps don't need batteries or separate inverters. They run directly off of the solar modules, and but batteries can be used to extend pumping times during the solar day. Again, I'm not going to go into much detail there, but obviously PV can charge batteries, or any source can charge batteries, and then you can run pumps off batteries too. These systems generally run anywhere between 12 and 400 volts DC. Some are even higher, but that's primarily the range of most of them are done at. And pumps are available for pumping water from most water sources that are out there, whether it's wells or ponds or streams, irrigation ditches, catchments, and can be used in a variety of situations, whether it's household water or irrigation, livestock, transferring water from tank to tank, fountains, aerators, swimming pools. I'm not going to go into too much about things like swimming pools today, but obviously a pump is a pump and can be used for a variety of things. Some pumps do require filtering. Others can work with dirty water. It depends on the pump design. I'll go into some detail on that. Generally, PV direct pumps are used to fill storage tanks and cisterns during the day. And the reason for that is that since you're pumping direct off a PV array, the pumping speed or the quantity per minute or over a period of time is going to vary depending on the time of day, the intensity of the sunlight, solar resource. So PV direct pumps are generally used to just fill storage tanks because of the variable nature of them. It's not often used as direct usage because you can't guarantee pressure or volume at any particular time. Again, typically non-pressurized tanks might be large plastic tanks like shown in the picture. It could be concrete tanks or any kind of cistern. Flow is variable depending on the time of day. Pump's going to start slow in the morning and develop to full speed at noon and then taper off in the afternoon. Performance is measured in gallons per day. This is a kind of a big issue. A lot of times I get requests for pumping and the only information I'm given is that they want a certain amount of gallons per minute. But gallons per minute does not have a huge relevance here because we're looking at accumulated water over a day, not just instantaneous delivery. I'll get into some more detail on that too. It's usually best to have a storage tank that can hold several days worth of water because, again, you can't guarantee the sunlight on any particular point in time or any particular day, so you want to be able to store water for your use. That's the purpose there. And they can be used for direct irrigation, mostly in terms of things like flood irrigation and even drip sometimes. Things like sprinklers require set pressures, and so that's not going to work very well on a PV direct application. There are all kinds of storage tanks available out there. Plastic tanks are actually fairly cheap. Concrete tanks or cisterns, fiberglass tanks, excuse me, those kind of things. And it is cheaper, easier, and more reliable to store water in a tank than energy in a battery. And that's one of the reasons why these systems work so well, is that they can be rather inexpensive with few parts and be very reliable that way. And storing water, once you get the water out of the ground, you have it for use. So it's very reliable on that point. So determining how you're going to design a system, there's a bunch of information you need to collect. Obviously, site location, the latitude, climate, solar insolation data, shading, trees, all kinds of issues that you have to deal with to get enough power to the pump. Need to know what the water is used for. That often affects the choice in pump or how the pumping system works. Seasonal water usage pattern. There might be a very high use in the summer and low use in the winter, or even vice versa. So we need to know that so we can size it properly for the time of year where it's most needed. And obviously the water source, whether it's a well or an open channel or catchment or a stream or a pond or any source, we need to know that. And we're going to need to know the water volume provided by the source. If a well produces 10 gallons a minute, for instance, we don't want to put a pump down that does 50 gallons a minute. We pump it dry. If it's a large water source, like a body of water, that may not be much of an issue because there's plenty of it there. But we certainly need to know if there's a limitation on a source of water. And the water quality, is it clean? Is it sandy? Is it dirty? Is it, potable water for drinking? Those kind of things. And then we need to know the pumping head or lift. And that's the well depth or the elevation difference between the source and the tank. And so that's the primary function of the amount of energy required. It takes a lot of energy to lift water, out of gravity. So that's a very important point that we need to know about. And I'll go into more detail again. So what is head? Head is also described as lift, or the amount of elevation change that the water needs to make from its source to its end point. So we need to know that. It's the amount of feet or meters that the pump has to lift the water. It's an elevation change, not the pipe length to the tank, although pipe length does have some effect, I'll mention that later. But first we need to look at the static head, which is just measured a variety of ways, from where the water source is to where the end point is, and that's with no water flowing, but the actual elevation change that we need to get to. Lots of ways to measure it. Altimeters work real well. GPS devices are fairly accurate. USGS maps are not super accurate, but they can help if that's the only information we have. Now then there's dynamic head, and that is the static head, which is the actual lift, plus any friction losses in the system that we have to overcome in order to get the water from point A to point B. The amount of friction that you have inside of a pipe when the water is flowing through it is going to depend on the type of pipe, the size of the pipe, the length of the pipe, how many fittings are in the pipe, and whether there's 90-degree bends or other things that would cause more loss of flow through the pipe and create friction. I have a website link here to a calculator, but there's a number of them on the internet, and you can get charts for different types of pipe. So again, in terms of total static head, we're looking at the actual lift distance from the water level of the source to the top of the storage tank. We want to be able to fill the storage tanks. We look for the top of the tank. The pump can be below the water level in the well, but it only takes energy to lift water from its standing level up to the tank. So, for instance, if in a well, if the water level is 50 feet below ground, the pump might be at 100 feet. The static head is only calculated from that 50-foot point, because that's the point that we're actually lifting water from, no matter where the pump is actually located. Pipe friction losses, again, water flowing through the inside of the pipe is going to create some friction. The larger the diameter of the pipe relative to the amount of water moving through it is going to create less friction. So there is a lot of advantage to sizing a pipe larger, especially if you have long runs of pipe. And this is showing a typical chart for Schedule 40 PVC pipe. That's one type of pipe you might use. If you use like black poly pipe, that's going to have a different amount of friction loss in it. For one thing, with poly pipe, the fittings fit inside the pipe and create some turbulence and some restriction at that fitting point, whereas in PVC pipe, the fitting is on the outside of the pipe, so it doesn't have any restriction on the inside diameter. So PVC pipe is generally a better choice in terms of friction losses, but that somewhat depends on what the length is and size of the pipe and the amount of water you're pumping. So there's lots of different ways you can choose different pipes to use. Head in feet is a direct relationship to the amount of pressure in PSI. and the factor is 2.31, and that's calculated at sea level. That does change with elevation, and I'll go into that a little bit in another slide. But essentially, if you know what the head and feet is, you can divide that by 2.31 to get the amount of pressure required to lift the water up to that height. Or conversely, if you have a figure for the pressure in PSI, you can multiply it by 2.31, and that'll tell you how many feet of head you're doing. So for instance, if you had, say, a pipe full of water and a pressure gauge at the bottom of the pipe, and it said 100 PSI on the pressure, that would mean that that pipe is the head of that pipe is 231 feet to the top. And be sure to use the same units when adding static and dynamic pressure components. You don't want to mix components that just confuse you. That was pushing water up a hill. Now, it's simply a function of the power of the pump to do that. However, pulling water, like sucking water from a source with a surface pump, relies on atmospheric pressure. And there is a limit to that. Theoretical limit of sucking up water is 33.9 feet, but we don't live in a perfect world, so there's really no pump that will do that. And really, as a practical measure, 20 feet is really the maximum that you can suck water with a pump. So if you're not using a submersible pump, you need to make sure the surface pump is as close to the water surface as possible. It takes a lot more energy to suck water up than it does to push it. So you want to be able to try to reduce the amount of suction lift as much as you can. You know, and in the diagram here showing a straw, now it's an interesting point here is that, you know, if you take a straw and you put it in water, the water is going to come up inside the straw up to the water level. It just does that through atmospheric pressure, obviously. And then to suck higher takes some energy to do that, to be able to pull it up. But there, again, there is a limit. The practical limit is 20 feet. Some pumps will do 20 feet, some will do only 10. It depends on the type of the pump. So there are many different types of pumps available. Depending on what you're using it for, there are a number of ways to choose which one is going to be your best pump for the location. Surface pumps need to be, again, located no more than 20 feet above the water surface. You typically subtract 1 foot of that distance for each 1,000 feet above sea level, and again, that's just a function of air pressure. And actually, weather can affect that too, but I think that's pretty much calculated in with the 20 feet. And those kind of pumps are used for very shallow wells or pumping out of ponds, streams, or spring boxes, other storage tanks, etc. Submersible pumps are installed below the water level, so there is no suction, essentially. It's a flooded section, so the pump doesn't have to overcome that. You also don't have to worry about air leaks and other things affecting that. So submersible pumps can be somewhat more reliable, or at least don't have to be checked as often. And they can be used to pump surface water with some special design considerations. Obviously, if you put a submersible pump, for instance, in a stream, you have to make sure that that pump's not going to wash away during a storm event and that kind of thing. You also want to make sure that you have some fairly clean water. Jack pumps can be used for very deep wells. There's really nobody that I can find out there that's actually manufacturing a direct product for that, but jack pumps are the kind of pumps that are used like in the oil field business. You see them in oil fields where they, you know, have this kind of up and down motion with an armature, and but that can be used for very deep wells. It uses a piston type mechanism very similar to what the old wind pumper, you know, farm style wind pumper pumps use, but can go very deep if you have a well that's beyond the capability of submersible pumps. And then there are circulation pumps, which are just used to move water around in a closed system, such as hydronic heating or swimming pools and other uses like that. Very often don't require a whole lot of pressure, especially in a closed loop system. So let's go into some details of some of the different types of pumps available. Centrifugal pumps essentially just move water by spinning it through an impeller. The water enters the center of the impeller and through centrifugal force is forced to the outside as the impeller spins. And they tend to have very high output but relatively low pressure. There are ways of gaining pressure by just adding more impellers in series. So the pressure from one enters into the second impeller, which will add pressure to it. And as you can see from that cutaway of the submersible centrifugal pump on the right side, there's a whole stack of impellers on the top there. And that's how you were able to get more pressure out of a centrifugal pump. They tend to require higher RPMs to run. Obviously, running at just a few RPM, you're not going to get any centrifugal force, and you're not going to be able to pump much water. Many models do require linear current boosters. What a linear current booster does is it can take incoming voltage at low amps and drop the voltage down and boost the amperage, somewhat like an MPPT controller would do. And what that can do is at least get the pump spinning. Again, at lower voltage, it's going to be lower RPM, but at least the pump is spinning and you don't end up with a locked rotor on the motor, which can overheat the brushes. Another type of pump is diaphragm pumps, and they operate by using a pulsating, flexible diaphragm to pump water, typically with a set of valves in them, not much different from an automobile engine, for instance. They can pump moderately dirty water because you don't really have rubbing surfaces. You just have this rubberized diaphragm that's pulsating back and forth and pumping water. So it can handle some dirt. They can run dry without damage, although you don't want to run them dry for too long a period of time. You tend to overheat them because they are water cooled. They're positive displacement, although I actually call them semi-positive displacement because there is some flexibility in the diaphragm. So as you gain pressure, typically there is some change in the volume output over low pressure situations. They can pump at slow speeds, very much like a positive displacement pump. Even at 1 RPM, you still get a pulsation. So there is some water that comes out of the pump. Linear current boosters are definitely required with these. So there's pump controllers or just direct LCBs available. We have a number of options in our catalog for that. Rotaryvane pumps are another type of pump that are very efficient and positive displacement. And it moves water with a rotor similar to a paddle wheel. You can see from the picture in the upper right that it has these vanes that could move in and out of that off-center rotor, and that acts as a paddle wheel and pushes water. They're very, very efficient and can do somewhat high head, up to 440 feet with the models we carry. They do require a linear current booster. They're DC brush motors generally used. They do, however, require very clean or finely filtered water. Two of the examples here are the Dankoff slow pump or the Flow Life booster pumps, and they require filtration down to about 10 microns. You do have some rubbing surfaces on these, so any sand or grit in there is going to wear it out prematurely. Could also block the movement of the veins and prevent it from pumping. Piston pumps are another option. It is very much like a gasoline engine, except that instead of pumping air and gasoline, it's pumping water. But same kind of principle. You have a reciprocating piston and a set of valves, and they can also run at very low speeds and still pump water. They're very rugged and reliable. You do need a linear current booster with these also. So in order to get maximum output from a PV array, that's required. It wouldn't be required on a battery system, but certainly PV direct. And and again, it can also run at slow speeds. And these pumps are great for moving higher volumes of water over long distances, pushing through long pipes, and that kind of thing. And then we have helical rotor pumps, which are very popular these days for submersible well pumps. And they move water through a progressive cavity action of a fluted rotor and stator. They act as positive displacement, although again there is some flexibility in the stator that does have some effect on its flow rates at different pressures. They can get to very high heads. The Grundfos SQ Flex pump, for instance, can go up to 800 feet on some models. And they are able to handle some somewhat dirty water, but again, there is some rubbing surfaces, so you don't want a lot of sand or grit in there to do that. But it will actually handle some dirty water and last for a very long time. Another type of pump that we do carry is a very specialized pump called a high lifter pump. And what it can do is it actually uses water pressure to pump a portion of that water further up the hill. I'm not going to go into a whole lot of design on this. It's a very specialized pump. Essentially, you have to be able to drop water from the source downhill to the pump, and that provides pressure to the pump. A portion of that water will then be essentially pumped uphill by increasing its pressure. It's essentially a pressure increaser. So, a portion of that water goes up. So, for instance, there's a 9-to-1 ratio pump. If you have 9 gallons flowing down to the pump, 1 gallon of that can be pumped further up the hill. The other 8 gallons come out of the pump and just come out on the ground. So these are very good for like springs or constant water sources in mountainous areas, and can be very reliable. They just work 24 hours a day with no power input. They just use the pressure of water. We have a page in our catalog that describes that more fully. But those are wonderful pumps that have been made for about 25 years and been very successful. So when we're designing a pump system, we need to figure out what the total head is, and that's going to be the static head, which is the depth of the standing water level in the well, plus the height from the well surface to the top of the tank. And we need the dynamic head. So we need to know what the linear distance is between the pump and the storage tank, and to be able to figure out the pipe friction. So we're going to need to know what size pipe to use, although we may determine the pipe size by determining the friction loss in the pipeline, depending on its length. We need to know what our goal is in terms of required production. So how many gallons are used per day? What are the requirements? And are there seasonal variations that we need to be aware of when we're sizing these systems? Storage tanks should hold 3 to 4 times the daily requirement. That way you can get over cloudy weather or several days of cloudy weather or just low pumping situations and still have the ability to have the daily water amount. Plus your water use may vary day to day. So you want to be able to store that water and be able to use it in a volume that you need per day. And the requirement for the daily gallons per day, of course, has to be met by the source. So we need to know what the yield of the well is. And if it's a low yield well or water source, we're going to be limited by the yield of that well. No matter how much water we may want to pump, if the source is not there, we don't have the actual volume to do that. So we need to know what that yield is. We need to know if there's filtration required, what the water quality is. In terms of location of, say, a well or a source, it's good to know if there's any other potential power source. If a well is close to a house, let's say it's an off-grid house, it has a PV battery inverter system already in it, and the well is close to the house, it might make more sense to just run that pump off the household system rather than put another set of PV modules out in a field where they're just sitting there and maybe not even doing anything. If the water tank is full, you don't have more water use, those modules are sitting there not doing anything. It would be better to have them on the house helping to run house loads and charge batteries. However, of course, if the well is 1,000 feet or hundreds of feet or thousands of feet away from any other potential source, then it's going to be better to put its own power system out there. We're going to need to know what the local weather conditions are, how much solar insolation we get at the site, whether there's any shading issues there, whether we have to worry about pump freezing issues. There's a lot of issues in general with water pumps and plumbing, of course. I won't go too much detail on that here. But we certainly need to know all of those aspects in order to properly design a system. And if it is a well, we need to know what the well casing diameter is. So make sure that the pump will fit down that well. Obviously, you can't put a 6-inch diameter pump down a 4-inch well, so we need to know that. And then we need to measure where the static or standing water level is in the well. There's a number of ways to do that. The simple way is just a fishing line with a weight and a float and measuring tape. Just lower a weight and a float down until the float sits on the water surface and the string goes slack, and then you can mark that and pull that up and measure that. That's a pretty simple way to do it. There are commercially available measuring tools out there that essentially just use an ohm meter essentially that's just looking for continuity in two wires. When two wires contact the water, it's going to be continuity there. So that's another way to do it. Here's an example of a submersible pump system using the Grundfos SQ Flex, showing the components. It's really pretty simple. There's a PV array. There's a controller, or at least an on-off switch, which is what's shown here. The IO50 is really just an on-off switch box. Submersible pump and piping up into a storage tank. It's a very simple system. Sun comes up, the pump starts. Sun goes down, the pump stops. There's really not much else to it. There are various controls that Grundfos does have to do other things, such as turn the pump off when a tank is full, or be able to connect a generator to it, or other things like that. Now, when you're drawing from ponds or lakes, there's other design considerations. Obviously, you need to know the total head, the pipe friction losses. You're going to need to figure out what the actual source is. So the area and water depth of the lake or pond can give you an indication of how much water is there. How is the water replenished? Is it spring-fed, or just storm-fed, or just storage of some sort? Some people actually pump out of wells to fill ponds, and that might be another way to do it. Does the water level change seasonally? That's really going to have more to do with if you have a surface pump, and it's say normally at 10 feet of suction lift, but the pond surface area goes down, you might end up exceeding the suction capability of the pump. So you need to know that. You need to know what the water quality is. One thing about pumping out of things like ponds is you have to look for problems like algae growth and leaves and other things like that. Obviously, location. For the PV array, you want to get maximum power from the array, so you want to site it in a place that gets good sunlight. And then you have to figure out how you're going to control it, whether it's a float switch or pressure switch or some sort of overflow. One way to do something like from a pond is to pump into a tank. The overflow from the tank can be another pipe that just goes back to the pond. So you don't really have to turn the pump off. You could just have an overflow like that. Drawing from streams and rivers have other considerations, very similar to a pond, but you also have to worry about pumps being washed away. If it's a submersible pump in the water, that's obviously a big issue. But even a surface pump on the edge of the water, you need to make sure you site it outside of a flood zone, or be able to move it in case of a flood, that kind of thing. So you're going to need to pay attention to that. Flowing streams also tend to have a lot of debris that runs down them. So you have to worry about or deal with clogging intakes, or screening the intake, or just making sure that you're not going to get plugged in there by some floating debris. Obviously, the location is going to depend on the weather conditions. And again, there's other ways to control the mechanism of the pump, whether it's float switch or float valves and pressure switches, or directed overflows. Drawing from tanks or cisterns is generally easier because you have a set amount of water. Pump can generally be placed next to a tank, and so you're not actually sucking up from a water source. You have what's called a flooded section, which prevents airlocks from happening in there too. Or you could even put a submersible pump in a tank. There's a number of ways to do that, to go tank to tank. Again, same kind of issues of water quality and location for the PV array, and the control mechanism. Now, typically when you're pumping from one tank to another, you might need to use two float switches, one in the first tank to turn the pump off if the water level in the tank gets too low for the pump, or the tank gets empty, and another float switch in the tank you're pumping to that may turn the pump off when that tank is full. So it often requires two switches in this situation, and are typically run in series, so that both switches have to essentially be connected on before the pump works. So in terms of sizing PV arrays for direct pump systems, the nameplate array size should be at least 20% larger than the rated power draw of the pump. So, for instance, if a pump is rated to draw 1,000 watts, you want to have at least a 1.2 kilowatt array to do that. However, increasing the size of the array is going to increase the reliability of your pumping, because you're going to be able to produce that 1 kilowatt in less light. There's virtually no limit to the amount of PV you can put on a pump. A pump will use a motor. It'll just draw what it needs to draw, and it just won't use any excess power that might be there. So, for instance, if you had a pump that needed 1,000 watts to run, you could theoretically put a 10,000 watt array on that. A 10,000 watt array would produce 1,000 watts in only 10% of full sunlight. So that would mean that you're going to, be able to pump even in cloudy weather, or certainly early in the morning and late in the afternoon. Obviously, there's a huge cost difference between a 1.2 kilowatt array and a 10 kilowatt array. But other than that, there's no other design considerations for the pump itself. It is true that if you have an oversized array, the pump is not going to be as big of a draw on that array, so the array is going to operate at a slightly higher voltage because it's not being loaded down as much. But that's, generally the pumps are rated to handle voltages that will be all the way up to open circuit on the array, so it shouldn't be a problem there. And the pump will only draw the power that it needs. It's analogy you have is if you plug an AC pump into the grid, for instance, you might have Hoover Dam sitting behind. It's a huge power source. The pump is still only going to draw whatever wattage it needs. So the actual available power of the power source is not relative to what the pump will actually consume. You do have to look at seasonal variation. Obviously, there's reduced solar resource at the winter solstice or any time during the winter, so you need to make sure your PV array is sized enough to be able to provide that amount of power needed to pump the amount of water needed at that time of the year. And the linear current booster or pump controller only needs to be rated for the current draw of the pump, not the total array current. Again, the motor on the pump is only going to draw its rated amperage or wattage, no matter what the size of the PV array is. Trackers are another good way to increase output. Obviously, a tracker is following the sun is going to give you a more even amount of power over the course of the day than just a fixed array is going to do. You can also just oversize the array. There's another way to do it, so you have to look at the cost-benefit analysis there, how much space you might have to mount the array. If it's limited space, a tracker can be an excellent way of increasing water volume per day. So I'm going to run through an example here, a couple of examples actually, and just give you an idea of the procedure used to size a pump like this. This is going to be a residential water system that is lucky enough to have gravity flow from the storage tank to the house. So we don't need to pressurize the water for the household use. Gravity is taking care of that. In this case, as this example, we're looking at a 200-foot deep drilled well with a 6-inch casing. The static water level in the well is at 100 feet below ground. Typically, when you drill a well, you might hit water at a certain level. Well drillers will go deeper than that and allow for some storage essentially in the well casing. And depending on the geology of the site, there's a certain amount of underground pressure that will actually push water up through the pipe. If there's enough pressure, you get an artesian well. So that can actually be a situation where the water comes right out through the top of the well. It's fairly rare, but it does happen. There's very often a static level that's higher than the actual water inlet underground. In this case, we're assuming, or we've tested, that this well can produce 20 gallons a minute, so there's lots of water there. Storage tank is located 100 feet above the wellhead, and that's, again, vertical height, not distance. So total static head then is 200 feet, and we're going to assume a winter requirement of 1,500 gallons a day and a summer requirement of 3,000 gallons per day. And we're using it both for domestic and irrigation usage. Storage tank is, again, it's uphill, providing enough water pressure. And again, you can use the same 2.3 0.31 formula to figure out how much pressure you get from a tank. So if you're looking at 50 pounds of pressure at the house, then you need to multiply the 50 times 2.31 to see how high that tank needs to be up on a hill to get that kind of pressure. It works the same way coming down the hill as it does going up the hill. And in this particular site, we get about 3 kilowatt hours per meter squared in the winter and twice that amount in the summer. We're just using this as an example. So one of the easiest ways to do it is in our catalog, we've developed this chart for the Grundfos SQ Flex pump, for instance. So you can see the head on the left side and choose your head ratio. In this case, it's 200 feet. And then moving to the right along that row there, there's a variety of options in pump size, pump model, and in the PV array size, which is up at the top, to get a certain volume of water per day at that head. This chart was developed with data from Fresno, California, which is a very sunny site. So the kilowatt hours per meter squared needs to be adjusted to each site. But in this case, according to this chart, with 4 PV modules, and we're using a 250 watt module in this case, certainly could be a 260 or a 270. It's only going to be a little bit better than what the chart shows. But it's roughly 1,000 watts of PV in this case, and the blue circle there. And it's showing in a very sunny spot like Fresno, it's going to average about 4,200 gallons a day in the summer and about 3,000 gallons a day in the winter, with a peak flow of 7.6 gallons a minute using the Model 11 SQF2. Now, we've chosen a pump model in each one of these squares that will give the maximum output. It doesn't mean that another model wouldn't work there. So, for instance, if you look at the 3-module column, you'll notice that it's a Model 6 SQF2. That pump will still work with 4 modules at that height. It just won't deliver as much water as the Model 11 pump would with 4 modules at that head. That's all that means. So, we look at the chart there. We're seeing that it does roughly 4,237 gallons per day with 7.8 peak sun hours. But we need to convert that to the 6 peak sun hour figure. So we need to figure out what the actual gallons per peak sun hour is in that design head. And we come up with 543 gallons per peak sun hour and multiply that by 6. We end up with 3259. This is not an exact conversion, but there's enough leeway in this that it works out quite well. The system, obviously, there's a lot of other variables in this in terms of high humidity areas will have less sun intensity. Higher elevation areas will have greater sun intensity. So there is some variation there. And then we need to convert also for the winter figure, and using those figures from the chart, and it actually ends up being 6.41 gallons, 641 gallons per peak sun hour in the wintertime. So it would end up with about 1,923 gallons per day average in the winter. But that meets our design criteria. We want to get 3,000 gallons per day in the summer. We want to get 1,500 gallons a day in the winter. So that pump and that combination with 4 PV modules will do that. That doesn't mean to say that you shouldn't add more PV to it to make the system more robust, which is what I describe here. So the conclusion here essentially is a 4-module PV array would provide sufficient water delivery, but 5 or 6 modules would be a more reliable performance. You may get more water delivered than what you need and have a float switch or some other mechanism to turn the pump off at that point. Top-of-pole PV mounts are a good choice for pumping systems. Certainly other mounts can be used, but top-of-pole mounts are really nice because they get the modules off the ground. Very often there's grass that grows up, or there might be livestock or animals on the ground. You want to be able to get the modules up above them so they don't get shaded or damaged. You want to place the pump in the well at least 15-20 feet above the well bottom to allow for some sediment. Wells tend to get better with age. They tend to deliver more water as they get used because you're sucking water out of the underground passages. and tends to clean out any debris or silt that might be in those passages. So when you drill a well, the well driller might tell you you're getting 10 gallons a minute, and a year later you might get 12 or 13 gallons a minute because you've actually cleared out the channels in there. But you want to have a place for that sediment to settle, and you don't want to bury your pump in there. Not only will it be hard to get it back out if you need to, but it's going to overheat it and clog it up. In terms of cable lengths, you can certainly use 12-gauge cable for lengths up to 200 feet and PV arrays of 4 or more modules. Otherwise, you probably want to use 10-gauge wire for deeper wells. If it's really deep, you might even want to use 8-gauge or even up to 6-gauge wire to keep your voltage drop down. That may be another reason to add more modules. Since you're putting the modules in series, you're increasing your voltage with every module you add, and that's going to decrease the amount of voltage drop in the wiring. So it might actually be cheaper to add 2 modules than it is to go from a number 10 wire to a number 8 wire, depending on the price of copper at that particular point. And with a Grundfos system, most systems use the CU200 controller with a float switch in the storage tank for overflow protection. Tank gets full, the float switch connects a circuit sent through a 2-conductor wire to the CU200, which then tells the pump to stop. With the Grundfos system, it's not actually interrupting the power to the pump. It's a power line communications between the CU200 and the pump. And it's actually a signal to just stop pumping. It doesn't actually shut the power off. So here's a list of equipment. The pump itself, obviously, in this case, is the Model 11 SQF2. CU200 controller, which is a weatherproof unit. It can be mounted outside, right on the pole or on some sort of stand. You'll need a float switch. We carry the Grundfos float switch. Essentially, it's a reverse action. It's when there's contact in the switch, that's when the pump stops, as opposed to contact to start it. Going to need 180 feet of wire in this case, an underwater splice kit. The Grundfos pumps have 3 wires that you need to splice to the longer drop cable, and that needs to be a waterproof splice. We typically also use a piece of larger heat shrink tubing to cover those 3 splices and to seal the outer jacket of the pump cable. And then you'll need some 2-conductor wire to run from the CU200 controller up to wherever the tank is for the float switch. We do recommend using shielded cable for that purpose to prevent lightning-induced surges, which can damage the CU200 and possibly the pump. Buried cables would help too, but a shielded cable is certainly a good idea. But there's no current really flowing through that wire, so it doesn't have to be a very big wire. 16 gauge or even 18 gauge is fine for even hundreds of feet. Grundfos says that their limit to the float switch is 2,000 feet, but I know of systems that are running longer distances and they work just fine. In this case, we need 4 to 6 standard PV modules. You can use more modules than that. The Grundfos pumps are limited to 300 volts DC. So in any places that get fairly cold temperatures in the wintertime, you're pretty much limited to 6 standard modules in a series string. In some warm winter areas, you can go up to 7 modules in a series string. But you can use more modules by just using multiple strings. So for instance, if you want to use 8 modules, that's 2 strings of 4, or 10 modules would be 2 strings of 5. 18 modules would be 3 strings of 6, for instance. So there's no limit there. You just have to make sure that the PV array is not exceeding the voltage limits of the pump in question. Obviously, you need a module mounting hardware. You need cable long enough to go from the PV array to the CU200. If the PV array is going to be a fairly long distance from the controller, you probably want to put an array disconnect switch at the array to be able to turn it off, because you are dealing with some higher voltage DC. Obviously, you need a grounding system. The pump itself has 3 wires. One of them is a ground wire, and that needs to be connected inside. The CU200 has connections in there for that. And then there's some optional controllers, such as the IO101, which can interface with a generator. So if the PV array is not keeping up with the required water consumption, you can run a generator, and essentially the IO101 is really just a transfer switch. It'll transfer between those two. Other things you need, obviously, just like with any well situation, you need a well seal, you need a safety rope, plumbing fittings, you might need perimeter fencing if you need to keep livestock or children or wildlife out, foundation for the PV mount, and then, of course, putting a well pump in a well requires a hoist or a crane if it's any more than maybe 100 feet. It's pretty hard to do by hand. And you need some zip ties to tie the cable to the drop pipe and make sure it's not flopping around in the well. Here's another example, is a much lower water requirement, just 300 gallons per day in the summer. It's just cattle or horses or some sort of livestock watering. Shallower well and a static level of 70 feet. Open pasture, there's plenty of sunlight here, stock tank. So a smaller pump such as the Aquatech SWP 4000 would be a great application for this. Typically a pump like this with even 150 watts would deliver somewhere between 500 and 800 gallons a day, depending on the location and the head. And so they're great for these kind of applications. And again, a very simple thing, essentially just a pump controller, which is an LCB, 100 feet of cable, underwater splices. In this case, this pump will run off a single module quite well. It really only needs 150 watts max. So a 250 watt module, 270 watt module is plenty of wattage. The pump's really designed to do nominal 24 volt array, which would be 72 cell in series, but it runs quite well in a 60 cell module, mostly because there's more wattage available there. It makes up for the difference in the voltage. Same kind of things, a mounting system, PV output cable, pipe fittings. These pumps are very light and easy to put in. There's a number of ranchers might have multiple wells and have the pump down one well for a few days and fill up a tank and then pull it out and move it to another well. That's a very common approach for large ranches. So that was quick. Obviously there's a big subject and hard to cover in just 45 minutes to an hour. So I would be glad to work with any of you on specific pump designs or answering any questions you have. And thank you for attending.
All right, great. Thanks, Brian. Let's go ahead and start off our Q&A session now. If you have a question, feel free to submit it through that question section on the right-hand side of your screen, and we'll get through as many as possible. If there are any extras, Brian can follow up with you afterwards. You can exit the webinar at any time. Just click that X, and don't forget to fill out the survey so I can send you a copy of the presentation slides. All right, and without any further ado, we'll get to some questions here. Brian, our first question, are there any pumps that can operate PV direct without an LCB?
Yeah, some of the centrifugal pumps can do that. For instance, the Dankoff Suncentric pump does not require an LCB. The main thing with an LCB is that what you're trying to prevent is you're trying to prevent a locked rotor situation where the pump is held steady and yet there's still voltage or current flowing through the motor, but not enough to actually get it spinning. And that's going to be a case when you have something like a positive displacement pump where there's already a full pipe sitting on it. Essentially you're pushing against a load as soon as it tries to go on. A centrifugal pump is a little bit different in the sense that it can spin in a water jacket without any friction. So just a standard like a single impeller or centrifugal pump can typically run without an LCB and not be a problem. It may not pump water until you get enough power from the PV array to actually develop pressure, but it won't be damaged by a locked rotor because there's no resistance at low speeds.
All right, great. We'll move on to our next question. We have a dealer looking for a recommendation on a communication system to use for a 3-pump system with 2 solar systems about a mile away.
Oh, okay. Well, communications is a whole separate issue. There's certainly a lot of equipment out there for like security systems, like remote cameras and that kind of thing. You know, X10 equipment and whatnot. It can certainly be set up. I've seen systems set up that have wireless communications to float switches, for instance. There's also monitoring systems that are out there. Grundfos does make some of that too. Kind of a broad subject. I could certainly address that on an individual basis and would be glad to do so.
All right. The next question we have, what is a jet pump, and do you advise using it with PV to power?
Well, you know, I didn't put any jet pumps in the presentation because jet pumps are not very efficient. So they don't tend to lend themselves to direct PV pumping. What a jet pump does is essentially takes a portion of the water pumped and sends it back down into a well to go through a small nozzle, creates a jet. And that creates a pressure differential that allows you to pump more water from a deeper depth than what you could actually suck. In other words, it relieves that 20-foot maximum suction depth. But because you're pumping some water back down the well to get more water out, it's not a very efficient process. It tends to take more power. They certainly can be used in these situations, but typically more used off of an inverter or a battery system rather than PV direct, because you do have to generate enough pressure, enough RPM to actually have them function.
All right, great. The next question we have, are there any special considerations in the design if there are freezing temperatures in the winter?
Yes. Well, obviously you don't want your pumps to freeze. So if the pumps are above ground surface pumps, you need to protect them from freezing. Freezing water will break a pump quite easily. Even a cast iron head will be split apart very easily by freezing water. You also don't want your pipes to freeze because you don't want to have your pump trying to pump against a solid block of ice inside the piping. So in those kind of situations, submersible pumps are a great choice because they're down in the ground where they won't freeze, and piping would need to be buried below the frost line. There's units called pitless adapters that allow you to actually tap into the side of a well casing below ground for the piping system, be able to come out below ground and go up into a tank. It can be a problem. I mean, certainly if you're in a very cold area, there's a lot that you might need to do. Underground cisterns would be another option. Yeah, I would certainly recommend talking to some local standard well pumping people if you have big freezing problems, because I'm sure they've worked out lots of variables and ways of doing things in that kind of climate.
All right. Great. Another question we have here. What installation rate would you recommend for sizing PV arrays for the Grundfos sizing chart in the Humboldt County?
Oh, well, again, that's going to depend on the depth of the well and the amount of volume you need. There's really no limit there. Even 2 modules can pump from a very deep depth, although you might not get a lot of volume out of that. The more modules you add to the system, the more volume you're going to get. But I think probably the most common setup with these is 4 modules on a fixed mount. 4 to 6 modules is really fairly common, although there's certainly lots of them out there with just 2 modules on them. Of course, with the low price of PV these days, it's not a big additional cost to add more modules to the system. It just makes it more robust. The more modules you have, the more robust the system is going to be.
All right. The next question we have, are all DC lift pumps brush type motors? Are there any permanent magnet type?
Well, the SG Flex from Grundfos is a brushless motor, brushless DC motor, which essentially means it's an AC motor. It's an induction motor, essentially has built-in inverter that's taking DC and converting it to a wild voltage 3-phase AC in there. It's really pretty much how you get a brushless DC motor. Most of the surface pumps are brush-type motors. There are a few models out there that are brushless. Brush-type motors have several advantages. For one thing, they can run at variable speeds very easily just based on the voltage. So the lower the voltage, the lower the pump speed. It makes a very simple system to run PV direct. It's much more complicated to do brushless, but it can certainly be done. There's a number of models out there that can do that, both surface and submersibles.
All right, and we're going to move on to our last question here. How do we test the water level sensor in a water well to make sure it's working properly before completing the installation?
Well, without actually running out of water, I don't know if there's really a way to test that. I mean, you can certainly lift the sensor out to where it sees air and you know, make sure that the system works. And that's about the only way I know to do that. You could probably do a continuity test. There's a number of ways that water sensors work. The Grundfos SQ Flex has a little sensor built into the ground wire, into the wire lead of the pump, and it hangs about a foot or 18 inches above the pump, and all it has to do is be exposed to air, and it will signal the pump to stop. Other types of sensors use typically 3 probes, where you'll have a very low probe. That's your essentially your common. It's always submerged in water, is typically even at or below the pump level, and then you'll have 2 sensors that are higher up. One maybe just above the pump, and that acts as your low water sensor, and then one higher up is your high water sensor, which is the point where you turn the pump on. So that's a 3-wire kind of control mechanism. The SureFlow 9300 pump uses a system like that. There are also aftermarket systems you can get that work on that too. What's happening more and more is electronic control. Some pump controllers are coming out now with electronic sensing. So essentially, if the pump sucks air, its voltage, its power curve changes. It takes less power to pump air. So as soon as the controller sees drop off in power demand, it essentially means that it's sucking air, and it'll turn the pump off. And then there'll be various times that are programmed or set in there, a waiting period to wait before turning the pump back on to let the well recover. Those are by far the most reliable compared to the sensor types.
All right, great. Well, thank you, Brian. That concludes the Q&A portion of the webinar. Thank you, everyone, for joining us for the presentation today. Just a couple of quick notes. There is the survey that will pop up after the webinar. It'll also be emailed to you, so if you could please complete that. I'll send you a copy of the presentation slides. We'll also be posting these to our YouTube channel after the series has ended, so keep an eye out for that. And don't forget to join us in 2 weeks for our next presentation in the summer webinar series, Selling Solar, Cash Lease, and All Other Residential Finance Under the Sun. And don't forget to check out our website for other training opportunities with AEE Solar. Thanks again, Brian, for your presentation. If you have any other questions, sorry, you can follow up with him directly. But have a great weekend, everyone, and thanks for doing business with AEE Solar.
Yeah, thanks for joining the webinar. Take care.